Welcome back to Lecture 9 for our computational biology course. As always, I need to remind you that we are being recorded and live streamed. Today, I am going to go back over and we'll do quick updates. We already heard one, but we'll do additional quick updates. And then I want to go back over some of the material that we covered last week where I think the slides were not presented very well. And so I spent some time trying to clarify some of the issues with secretion and absorption. And I'm sure Giuliano could update them even more, but we'll go from there. And then we'll see how far we get. I was hoping to get to chemotaxis today. I don't know if we'll get that far. I'd rather make sure everybody is following with what we've done, even if it slows down the coverage a little bit. So we already heard one update. If people want to quickly update me on their projects, we start with Connor.
So Andrew and I just met with Giuliano, I think yesterday. Yesterday, cool. I'm losing my sense of time. And we got persistent migration implemented for the single cell simulation. And we also talked about how to scale the lambda for chemotaxis, because the way that I implemented it doesn't work with Apache gradient, but now it should. So that leaves us, we still need to get the kind of like parameters balanced right, because the cell still keeps dying the way it's set up right now. But once it's balanced, I think the single cell chemotaxis simulation will be done, which means that we'll officially be ready to move on to multicellularity stuff and binding sites, which I think is, we're slightly behind the ambitious plan that we set out for, but I think that we're close enough to it that we're in a good place.
Great. Okay. So, Joel and Jackson.
Yep. This week I didn't have much time to work on the project. But we've been reading more papers. That's at least we're on my part to see how we can gather all the information together. Trying to understand pathways better is so complex that it's taking a little bit more time than I was expecting. But yeah, at least that's from my side.
Okay. Jackson, anything you want to add to that?
I started playing around with the equations that we had for the necroptosis module and CompuCell and trying to maybe make something with it. It's a little complex, but I think I'm starting to understand it better.
Okay, if you want to meet, talk about that, that's fine. Is there anything either of you want to show today? Or I should have asked Connor if there was anything he wanted to show. Connor and Andrew. Josh?
Yeah, so may I share my screen? 1 second. Okay. Can everyone see that? So I was able to get the simulation running. So it explores it pretty well. I think I just got it working. I think I need to like put some repulsion near the walls or something. So, because I see that it's like going, it like, it seems like it's getting attracted to the wall over here. So I'm not sure why that is, but it might be that I need to add walls or repulsions near the boundaries. Some things I was kind of confused about. I couldn't really find any documentation in the newest CompuCell. Some things like I'm not entirely sure what anneal and this flip to dim ratio does. It was in the original code.
Well, good. Those are good questions. Those are things that we don't use very much. They're still supported, but they're deprecated. They're both set to they're both set to be turned off the way you have them there.
Okay.
Anneal is something where if you turn on annealing, the display, and I don't know if it still works, it may have disappeared. The display is smoothed out in a particular way.
Okay.
As you know, when cells move, you can see pixels that separate from the cell.
Mm-hmm.
And there's an algorithm to get rid of those stray pixels. And that's essentially to clean things up before you publish them, which was put in, in the original Fortran code back in 1992. So that's how old that is. Flip to dim ratio is something that we might run into occasionally, which is that at the moment, if you look at your Python steppables, you can call something every Monte Carlo step, every 5 Monte Carlo steps, every 10 Monte Carlo steps. But what you can't do is call something 5 times per Monte Carlo step.
Mm-hmm.
And so the flip to dim ratio basically sets the the step of the Monte Carlo step to say that if you make it 5, then the things that are actually called every Monte Carlo step will be called 5 times per Monte Carlo step. Basically short,
Mm-hmm.
It basically subdivides the Monte Carlo step. Now, why it's called flip to dim ratio is obscure, but it's something that occasionally that gets used if there are timescales that are very different in a problem. In particular, if you're doing things like subcellular modeling where there are chemical reactions that have very rapid changes, you don't want to have to make your Monte Carlo step very short, because that's expensive computationally, and this allows you to do that.
Mm-hmm.
But it normally those are things we don't touch, and I didn't show it because by default now we don't put them in. They're available if people want them, but they're not things that we default.
Okay, but yeah, like you were saying, the way with the anneal set to 0 and the flip 1, they essentially do nothing. So I could get rid of them.
That's right.
Okay.
That's right. They won't do it.
Okay. Also, I couldn't really find, except for the original was written in 3.6. I found documentation for this connectivity plugin there, but I wasn't able to.
Right.
So is that deprecated as well?
No, I think that still exists. That's a tick box in Wizard. It again, that actually modifies the updating algorithm.
Yeah, but
so both of these things are basically ways of keeping the cells from falling apart.
Mm-hmm.
And that there are 2 kinds of connectivity, one of which is the connectivity general one, and one of which is 2D connectivity. And there are certain kinds of instabilities in this kind of model which allow cells to break in pieces. And that checks for that and prevents it from happening. Mm-hmm. And when you've got cells under tension, the way you do, where you have a very elongated cell, that can be pretty important. And so that one should work.
Mm-hmm. It works.
It does. I had a feeling that it didn't work that great, but glad to be wrong.
I mean, so before this, I didn't include it because I couldn't find it. So I was afraid it was going to break it. And then when I ran it, this just disintegrated. And so I think it works as intended, because now clearly they're forming, tubular structures and not just disintegrating.
There's a numerical, it's actually a physical instability called capillary instability, mm-hmm. Which is what happens when you pull on water and it breaks up into droplets. And the cells here are subject to capillary instability as well. and this is suppressing that.
Mhm.
And fundamentally what it's doing is it's checking that when you do an update, that you're not taking a single cell and breaking it into two disconnected pieces.
Mhm.
In 2 dimensions, there's a fairly rapid way of doing that. In 3 dimensions, it's quite expensive to make that calculation.
Mhm.
And the other thing you were saying is that you're seeing your cells stick to the edges of your container.
Mhm.
And that is a real effect. If you don't have periodic boundary conditions, the boundary of your container behaves as if it's a wall with a contact energy of 0.
Mhm.
And so if you're using positive contact energies, then things stick to it.
Mhm.
And so, yes, there are two ways around it, one of which would be to use periodic boundary conditions. But then, of course, your cells can migrate around the edge on the wrong direction, so to speak.
Mhm.
The other way to do that would be to build a wall and define a high contact energy with the wall if you don't want it to touch.
Mhm. Okay, yeah, because that's what they in the original code. It was not clear whether they used periodic or constant boundary conditions. But yeah, I was just thinking, like, if it's really, I want to model it like it's in an actual petri dish, and the mold can't just go go from one side to the other like that. So yeah, I think I'll just build a wall around it. So yeah, I'll do that, and then I think I will just try to recreate all of the simulations that he has in his paper, and then once I get that done, I think I'll probably try and meet with Giuliano to talk about actually like starting to build the NanoHub app.
I think that's very impressive that you've gotten so far and so quickly. We haven't really talked about the steering panel yet. So in NanoHub, we use also on desktop, but so far when we've changed parameter values, we've typically done it by hand, either through that steering panel, that model editor panel, or through editing the code itself. But you can pull up these IPy widget sliders, and those allow somebody to change parameter values as the simulation is running in a more controlled way, in a more GUI-ish way. And there are some demos of it in the demo packet. If you've used IPy widget sliders in Jupyter notebooks, places like that, then they'll be familiar. If you haven't done those kind of interrupt-driven user interfaces, it maybe takes a few minutes to get used to how to do it, because but those are pretty straightforward. The key thing is to decide what parameters you want the user to be able to change, and things like, do you want them to have to hit stop and restart, or could you have a live button that restarts the simulation under certain conditions? Change the volume of the cell, those kind of things. But implementing them is pretty straightforward. But that looks great. I'm impressed.
All right. Thank you.
Okay, anything else before we get back to lecture? So last time we did a little bit of dimensional analysis, and the key idea of dimensional analysis is just what it says on the tin, which is that you look at the units, the dimensions of your variables and parameters, and you assume that the functional forms relating those variables respect the fact that if you're adding things, the things you're adding have to have the same units. And so we looked at the diffusion equation, starting from the concept that the concentration has units of mass per volume. that a time derivative has units of per time, that a spatial derivative has units of per space or per length. And we derive from that the diffusion length, square root of d over gamma, the equilibration time 1 over gamma, where gamma is the decay constant, and the time it takes to diffuse from position A to B is the square of the distance between A and B divided by the diffusion constant. Now, one thing that dimensional analysis won't give you is numerical prefactors. So the diffusion time may in fact be 4 times distance squared over d, or distance squared over d times 2. Some of those prefactors will depend on, for example, the dimension of the problem you're working in, whether you're in 2 dimensions, 3 dimensions, 4 dimensions. But for the most part, what we care about is the scaling. That's something that we can get. And then we did a simulation where we had originally 2 weeks ago done linear gradient. Then we put in a decay constant, and we saw that the chemical field went from being a straight line, a linear concentration, to being an exponentially decaying concentration. And then we started talking about secretion and absorption. And I'd like to come back and do that presentation a little quicker, but do it again, because I think the way those slides work didn't cover all of the options. And there were definitely things people asked about in the homeworks that were not covered last week. So if we're going to think about secretion, so we are now going to have cells that are producing a chemical and secreting it into the chemical field. The first thing we have to decide is, I guess I should probably have listed that, who's doing the secreting, what cells are doing the secreting. Then we need to say where, with respect to the cells, where, with respect to cells, the secretion occurs. Then we have to decide whether the secretion is going to happen everywhere on the surface with respect to the cell, or only when the cell is in contact with another cell of a particular type. And then whether the secretion is happening at a constant flux, we're pouring chemical in at a constant rate, or whether we're keeping a level constant at the cell. And there is a general idea of a secretion plug-in in CompuCell, and we're going to need to specify that in the ML. And there are 2 places you can do it, and they behave slightly differently. One of them is the secretion plug-in itself, and the other one is inside of the diffusion solver steppable. And there are historical reasons why this is the case. In both cases, we can do some control from Python, but the specific functionalities we're going to have access to will be a little bit different in the different cases. And the outcomes will be slightly different. Numerically, they give very similar results, but not identical results, which is actually really a bug. But all we can do is identify it at this point. So the first thing that you have as an option is when you specify a chemical field using a diffusion solver, you can define within the diffusion solver secretion data. And here is an example. I have inside of my diffusion field, I've skipped the basic definition of the diffusion field, secretion data. Secretion type equals bacterium. It could be any cell type that you have named. This is a constant rate and end of secretion. I could also have put secretion on contact with, here, a list of the cell types with which I'm going to secrete. And again, a constant rate. And I can also define a constant concentration boundary condition. Here I've said the type cell wall has always a value of 0.1 at its surface. One thing that can be a little bit confusing here is exactly where the secretion happens. And I'd encourage you to play with that if you use that option. The key idea, again, and we did explore that last week a bit, is the difference between a secretion at a constant rate, which is like pouring chemical in at a constant rate, and constant value, where we're imposing a boundary which maintains that, the level of water in a dish. We can also define a separate secretion plug-in, and one of the things that's a little bit confusing here, perhaps, is that secretion inside of the PDE solver is in a steppable, and here it's inside a plug-in. But the syntax looks the same. Here we have to specify the field that we're going to be doing the secreting to or from. And then we can have, as before, secretion type, cell name, constant rate, secretion on contact with, same thing, constant concentration type, cell type, and amount. So the only difference between the other format and this one is that we have to say which field we're going to be secreting into or out of. The other one, we're inside of a field specification, so we know which one it is. So if we want to go further than that, and a lot of simulations don't need more than that, we might want each cell to be able to individually secrete, and individually secrete at a constant with different levels. If we have cells that are producing virus, and we're secreting into a virus field, some cells might be producing none of it, some might be producing a little bit, some might be producing a lot. And so we want to be able to have that secretion be cell-by-cell variable. And so there are a series of steps we have to go through to do that. The first one is that we need to specify in the XML that we're going to be using the secretion plugin and which field we're talking about. Then in the step function, we're going to have to get a reference to the chemical field and something called the secretor for the chemical field. And after that, we need to tell CompuCell on a cell-by-cell basis what secretion we're going to do. And so we're going to specify that for each cell one at a time. And of course, we could have different rules for different cell types or even in different individual cells. And we can specify for each cell where secretion is going to occur. And we have a bunch of options. We can be inside the cell at the boundary, inside the cell at the boundary when it's touching another cell type, inside the cell at center of mass, inside the cell, outside the cell at a boundary, and outside the cell at boundary with contact. So we've got 1, 2, 3, 4, 5, 6 options of that kind. We can ask the secretor to return the total amount of chemical secreted using the total amount option. And if you are secreting everywhere inside the cell, you can also specify that you want constant value rather than constant flux. So we have 1, 2, 3, 4, 5, 6 times 2, 12 options. And then this one gives us an extra 2. So there are 14 options. So let's walk through what you have to do. First, you have to put in the chemical field specification. Here I'm loading the secretion plugin. Field name. Here I've specified the secretion by type and a value. That's in the XML. And then in the step function, before I use the chemical field, I need to get a reference, a handle, to the field secretor object. And so there's a typo here because there's an extra space, so this would actually fail. I have to use the function self.get_field_secretor, and then the name of the field that I specified in the XML. I only have to do this once per step, so I don't want to put this inside of a loop. Usually this kind of reference handle will come at the beginning of a step function. Potentially also in a start function if you're using it, but mainly a step function. I can give it any name I choose. Here I've called it ATTR_secretor, but if I have 5 different fields that I'm going to be working with, I have to give them different names. Something that I recommend that unfortunately doesn't work at the moment in the NanoHub version of CompuCell is that the secretor object that's returned by self.getFieldSecretor is a pretty complicated object, and it's not everything that it can do is documented. People ask about this occasionally. I strongly recommend, and I know it's the fact that we don't have printouts available in NanoHub is a pain. You could write to a file. You could open a file and direct the output to the file. Maybe is the best option. Print, my favorite command in Python, dir. So if you dir an object in Python, it'll give you the object structure. It'll also give you all of its attributes and all the methods that you can apply to it. So if you say, gee, I can't remember all of those 14 options. Actually, there are more than that, but all the 14 options for secretion, I can dir attractor_secretor and it'll give me a list. It'll also give me a list of a bunch of other stuff I don't care about, so you do have to sort of dig through it a little bit. So one thing that is not very well documented and is not in Twit because it's fairly new, is that sometimes you want to be able to measure concentrations without having to change the chemical field. And in the old days, things were even more awkward. But what we do typically would be that we would say, okay, we'll take up a tiny amount of chemical, enough that it doesn't really perturb things, and use that to measure the field. However, we can do there are 2 commands that might be useful. Not all of those methods are implemented for different spatial configurations, but there is an attribute of attractor_secretor, which is called a function on attractor_secretor called total field integral, open close parenthesis. And that will return the total amount of chemical in the entire field. So if you want to rescale things by the total amount of material in the field, that number is available to you. You don't have to scan over the whole field and ask how much chemical do I have. That can be quite useful, especially if you're trying to adjust parameters, asking is the level I'm getting reasonable. You might ask how much do I have. The other one that you might want is how much is available within the domain of a cell. How much ATP is in my cell, how much glucose is in my cell. And in that case, I use dot amount seen by cell, and then a handle to the cell. And that will return the chemical field over the cell. This could be important, and we'll come back to it in the when we talk about absorption. We'll see that CompuCell provides only one numerical form for absorption. And if we wanted to calculate absorption by hand to do a more complicated rule of absorption, it's quite useful to be able to know what that amount is. So now let's do secretion. Let's just walk through the secretion rules, which we did last time, but I want to do again a little bit more carefully. So we're going to find that there are, I think it said 14 possible permutations of this. To do secretion, we will use the function, the method attractor underscore secretor. That's the handle to our field. Secrete, and then we have a bunch of possible commands. Inside cell at boundary, reference to cell, and the amount per time step. We have, again, the options: inside cell at boundary with contact, inside cell at center of mass, inside cell, outside cell at boundary, and outside cell at boundary with contact. And these are camel case with no spaces. We can also ask the secretor to return the amount of chemical secreted. And that seems a little bit strange, but this number actually is per voxel. And so the amount you secrete will depend on the size of the secreted area. And so it's not totally obvious. Here I've said result is attractor secretor, secrete inside cell total count is the command for that. I could call res something else. It's again a handle. However, res itself is not an amount, it's an object. And so to get the actual amount, I have to do res dot total amount. And perhaps it was unfortunate that total count here and total amount are not the same, either in camel case or in name. It would have been more consistent to have, say, total count and total count there too. And somebody who's energetic, I've got a demo in the Lecture 9 demos folder, which has all of these in it. I didn't actually do a dir on res on the output of attractor secretor to check on what the structure is. Somebody could do that. Again, the print dir object is always a good thing to do if you want to know what a complex object is about. Ideally, of course, our manuals and examples would cover everything, and Twit would cover everything, but they're written by humans, and so you can always try to introspect. Great thing about Python is introspection. Okay. So we can look at our cases again, and we did go through these a little bit last time, but I want to remind you of them. In many cases, and this is really inside cell is more of a secretion option than an uptake. I mean, an uptake option rather than a secretion option, but it's certainly possible to have it. If the secretion rate depends on the rate at which molecules cross the membrane of the cell, for example, we might want to secrete just inside the membrane. And I was saying to Giuliano that we really should do an exercise where we create a compartmental cell with a boundary, a membrane, with low permeability to do fixed law. If you feel like doing that while we're talking, you could demo that at the end of the class. And again, we have this possibility of uniform secretion or secretion only on particular surfaces of the cell. And the example here is I have a field that I've called attractor, ATTR. I get that handle to the field. Then on that handle to the field, I can do secrete inside cell at boundary for each cell. I can do secrete inside cell at boundary with total count, which returns the amount secreted to me. I can do secrete inside cell at boundary on contact with your wall or medium or something else, some list of cell types. And I can do secrete inside cell at boundary on contact with total count. And so the hardest part of this is remembering the syntax is consistent, but remembering which order those options come in is something that we have to do. And then amount secreted equals res dot total amount would give me the result. So that's secretion inside the cell at the boundary. Something that probably makes more sense for secretion would be having the cell secrete just outside the boundary, dump something outside. Exocytosis, which I talked about last time, would be an example of that. Everything looks the same, except inside is replaced by outside. So my options are outside cell at boundary, outside cell at boundary total count, outside cell at boundary on contact with, and outside cell at boundary on contact with total count. So it's verbose, but at least it's orthogonal. And this is one you use quite a bit, especially if you have something like a sheet of cells that are secreting into extracellular space. Any questions about that so far? Is that making sense? We covered this, but again, the slides needed some cleaning up, so I wanted to do it again.
I think I have a comment. On the project that I was doing, I think I secreted in a different way because I didn't know about these tools. And I just said a point outside using the cell, but like a point, a number of voxels outside the cell, start a secretion instead of going, I know that is not the best way since now I see that there is a tool that does the same thing, but I just wanted to mention.
Right. I strongly recommend against hand manipulating voxels, mainly because Python is slow when you do loops. And so iterating over all voxels in the image is slow. And so you're much better off using the C++ instantiations of those methods. They exist and they're made available, but I don't recommend doing it unless you like sitting around waiting for your computer to do needless calculations. Now, to be fair, if there happens to be a NumPy function that does the thing that you want to do to the field, NumPy generally runs pretty fast. But Giuliano says not so fast.
Well, it is fast, but there is the interfacing with CompuCell, and that I don't
That's
know.
True. NumPy. So NumPy fields are not NumPy arrays because they're swigged C++ objects. So you're right. You're better not to do that.
Yeah, maybe Alex knows more about this than I do. You've been looking at the guts of CompuCell a lot lately.
But those are good points. But this is why, because of the question of things like what you said, Joel, I really want to make sure that we go over this because I wasn't aware of all of these options myself. I had to dir it and say, oh, they added a new feature. Okay. The other options that we have are secretion everywhere inside of the cell. That could be something where, for example, the cell is synthesizing a chemical everywhere in its volume. Or we could imagine that the cell is representing the top surface of a tissue. And so the volume that we're simulating is actually imagined to be just above the surface of the cell. Typically, things are actual secretion happens outside of the object, but in a two-dimensional simulation, the volume in the diffusion solver may actually be thought of as above the volume that's being simulated for the cells. It's what we call a 2.5D simulation. In that case, we have attractor secrete inside cell, and we have some other options which we did not have for the others, all of the others, which is secrete inside cell constant concentration. And we saw those constant concentration options when we defined secretion in the step in the XML. Constant concentration means that instead of providing constant rate, we're forcing a boundary condition on the chemical field. And we'll play with that in a minute. And we can also do result attractor secrete inside cell constant concentration total count. And I've actually never tried that one out. But I think it could be interesting because if it works properly, it'll tell you how much chemical do you have to secrete to make this field stay constant. It may or may not actually work that way, but that's what it should do.
I think I by accident added that as an exercise in the homework.
Oh, great. And the last one is to secrete at the center of mass of the cell, at the single point at the center of mass. And that can be done either with or without keeping track of how much. And I recommend not using that. There are two reasons you might use it. One is that it's faster than the other methods. The other one is that there are a lot of software packages that only can do that. They can't do all of the other ones. And so if you were trying to exactly replicate a simulation from somewhere else that happened to do it that way, you can. But when you do this, you'll create a big spike of chemical at one point, and then you depend on diffusion to spread it out. And so you'll get something typically that's not very biorealistic. I mean, you could imagine, of course, I stick a needle into somebody, I inject a chemical at one spot, and I want to see how it spreads out. That would be the equivalent of this.
Is it possible? Sorry, is it possible for multiple points in the membrane, in the cell membrane, to secrete?
No, not with a single cell.
Okay.
We could implement that, but we would have to build a more complex structure. The reason for that is that the membrane is not an object, and so you can't automatically attach attributes or properties to the membrane because there isn't an object to attach to. If you want to do something like that, you would have to take your cell, subdivide it into subcompartments, and then you could have certain subcompartments secrete and certain not. If you do that in 2 dimensions, it's not too bad. In 3 dimensions, it becomes computationally very expensive. But we have had in some of the hackathons we did in the past year or two, some of the students have done that as an example where you create, but then your cells become fairly large. You need enough voxels in your cell that it makes sense to say that you have different voxels behaving in different ways. But it's a good question. Certainly, biologically, it can be significant. One question to think about always is, we talked about the diffusion length. And typically, chemical concentrations don't change very much over distances that are shorter than the diffusion length. And so if the diffusion length is on the order of a cell diameter, then the chemical field I get secreting at a few points on the cell membrane rather than everywhere is going to be about the same. If the diffusion length was the thickness of this black line, then if I secrete at one point and not over there, I'll get very different chemical concentrations. And so the ratio of the diffusion length to the scales that you're interested in is very important. So in that sense, that's an excellent question. And you'll see that if you do physics and you do what are called multipole expansions. If I ask the question, what is the gravitational field of the Earth, of a spherical object, I use Newton's law and I get it. If I ask the question, what's the gravitational field of two spherical objects like the Earth and the Moon that are near each other, the answer is that if I'm close to them, I'm attracted by both independently, and I have some complicated force from gravity. If I go very far away, I could treat the Earth and the Moon, clump them together, and it'll behave as if it were just a single particle, or single planet, with the mass of the combined system. And so you have to ask the question, how much spatial variation is occurring over the length scales in question, and that comes back to the diffusion length. If the diffusion length is short, then the kind of thing that you're talking about may be very important. The diffusion length is 5 cell diameters, then it probably is less important. Good question. Okay, so why don't we come back then and do a quick exercise where we create a field, create a single frozen cell in the center of the simulation domain, create a chemical field, you call it oxygen if you like. Include the secretion plug-in, create just that single cell, again, at the beginning. Here we can set the diffusion constant to be 1, the K constant to be 0.01. What does that mean the diffusion length is? What's the definition of diffusion length? There are very few things, there are very few equations that I will ask people to remember. And you can derive it because of our discussion of dimensional analysis, but
It's d over gamma,
almost.
Square root.
square root of d over
Square root of d over
yeah,
gamma.
yeah.
So if this is picked, 1 divided by 100, so 100 square root is 10. So the diffusion length of 10 voxels. Okay, and so why don't we do this in the XML? Try uniform secretion and constant concentration and see how they differ. And if you have your old code, which I hope you do, to plot the concentration as a function of position, you could look at those. And if you if you can get that done very quickly, then you could do some of the Python options. You could try secretion inside the cell, secretion at the boundary, secretion inside the cell with constant concentration, outside the cell at the boundary. On contact with doesn't make any sense if we only have one cell. So maybe that there should be an exercise where we have 2 cells and you see the difference when you have contact and secretion on contact with. Okay. I don't expect people to take too much time to do all of this possibilities, but I'd like you to take a little bit of time to try that out. Okay. For the person who's done already, I would suggest we're going on with further through the exercise. I assume you didn't do all of the examples. And for those of you who need more time, try to get to 1 example. I also, if you're stuck, while we were doing this, I regenerated the simulation myself, and I saved it in the student material folder under the name exercise 9._1. So if you get stuck and you want to try it out, that would be, it's there for you. I happen to be running CompuCell on my desktop here today, and so I have to reshare the screen if I want to show you my result, but let me try that. Courtesy of Zoom, the scaling is messed up in Player, which is one reason that I like to use the NanoHub version when I'm doing demos. But I thought it would be faster to do this here. Let me just show you what I got for that first exercise, and people can then keep working on it. So let me do a new share. So I created a single square cell. That cell is secreting at a constant rate. I'm plotting the concentration as a function of position across the middle. And I can see it's probably not that clear, but this is it's constant value, not constant rate here. Constant concentration is 0.1 at the cell top. And I can see the chemical diffusing out. And the diffusion length was set to 10. So I'll see that there's an exponential decay of the chemical concentration as I go away. So I think it's important that people try, even if you can't remember how to do the plotting the chemical concentration, if you can get the right-hand part of this to work, that's probably already enough. So people should keep working on that for a few minutes. If you have any questions, please feel free to ask me or Giuliano for help on this. In this case, I did this using the secretion plugin inside of the PDE solver. So I used the built-in secretion plugin. Okay, so here I went in and I changed to using the secretion plugin, the separate one. And now I'm secreting at a constant rate rather than a constant value. And you'll notice that it may be very tiny to see, but if I look at the maximum concentration of the chemical, it's now at 1, whereas before it was 0.1. And if I keep running, I will find that the maximum concentration will go up until it saturates at the secretion rate divided by the decay rate. So 0.1 divided by 0.01. So it should give me a saturation at 10, if I've got it right. No promises. Are people making a stab at doing this? I don't want to distract you, so I'll let you get back to it and give you a few more minutes.
Yeah, I think I have it working. It crashed
Okay.
the first time, but now, I mean, at the very least, there's something.
Okay. You want to show us what?
Okay.
That
So,
looks great.
yeah, so I think I have it working. And the only reason why these are slightly off is because I don't have the scales fixed right now. And I think for this one, I was doing which one did I end up selecting for right there? I think it was uniform.
Well, you can, if you don't remember, you can open in the left where it says model editor. If you open plugin secretion, it should tell you when you go to field, it should tell you constant.
Constant. Okay. Yeah, there we go.
Okay. So that looks good. You want to change it to constant, the other option is constant rate.
Sure.
And see what happens.
Do you want me to do that live or?
Sure, why not? It's one line change. Show everybody it can be done.
Okay. Let's see.
Oh, that is a constant. No, that is constant rate.
Yeah. Yeah.
Not constant value. Okay.
Okay.
So let's see. Do you have a separate diffusion secretion solve plugin, or is that?
I think that was the only.
I think it go up.
At least I didn't mean to. If I
Aha.
Okay.
That one's constant concentration.
I don't even know how I ended up doing that.
If you specify secretion twice, what happens? I don't know whether one overrules the other, or whether they both happen at the same time.
Yes, the top one overrules. I was having the same trouble here, and I had I had like, instead of cell, I had median, and the median takes over. I think it happens twice if you have different types, but if you have one type, I think the secretion plugin takes over.
Okay.
Okay, interesting. So did I do something wrong in my setup to get this? Because I'm trying to think back through my initialization in Wizard and figure out how
I think if you select secretion there, it will open up two fields, one for the data, secretion data, and then secretion there plugin. I think that's what happens.
Okay.
I think it's automatic. I don't think you did anything wrong. That's what I'm trying to say. I had the same thing.
So I think that the answer is that the code snippets don't necessarily know what else you've got. So the code snippet for the diffusion solver includes the secretion example in it. But when you do the separate secretion plugin, it doesn't know what else you've loaded, and so it doesn't throw a warning that you have duplicated.
I see.
Now, some things that kind of duplication is useful. For example, for initial condition generator, you could draw a blob here and a blob here and a blob here and a blob here, and those will work together. But in this case, it looks like constant concentration is winning out.
So if I comment this out, then it should.
I did the opposite, but try it. See what you can get.
Let's
Okay.
see what happens.
Back to that. Let's see. Okay,
So
yeah,
that's
that
definitely constant rate.
Yeah. Okay, so that's good to know. So you can comment out either one. You just need to make sure that it initializes both. That the one that you want is up top. Okay.
Okay. So that, I think, is a good illustration of the constant value and constant rate. Now, if people are still saying they need more time, can we help you? Can those of us who've got it help you get through this so that we can understand together how to do it? Because this is a pretty important and fundamental thing to do, and I also realize that it's not trivial. And so it was in the homework. And it's going to be something we're going to need repeatedly going forward. So if there are questions about how to do it, now's a good opportunity to step up.
I don't have any questions. I just want to, related to how to do it, but it's
Right.
more related to if we don't define where we want the secretion to happen, you always assume center of mass. Is that a default?
No, the default's going to be over the area of the cell.
The area of the cell? Okay. Because I did like a huge cell and it seems that is in the center of the mass of the cell.
So were you using constant rate or constant value?
For this one was constant value for this one.
That seems wrong. So maybe you can show us.
Or maybe I'm interpreting it wrong. That's
No,
also a possibility.
I think this is fine. I think exploring these things is something we can do together.
Okay. There. And let me see.
So one thing you know immediately
Uh-huh.
is if you look at the concentration field,
Yep. It's
notice
more
that
than
the
one.
value in the center is going up. That means it's constant flux and not constant value.
Oh. It's still going up. Yeah. I think it's stabilized at 44. Yeah, okay. It's now 1.
So if you switch in your code to say constant value, see what happens.
Oh. Just a second.
Look at the center of your field.
Mm-hmm. Yeah, now it's the whole area. Yeah, you're right. I did it wrong.
Well, that's why we play with it, because there are a lot of options, and it's. I mean, they are all potentially biologically meaningful, and there are other ones that one would like to have that are meaningful that we don't have.
Mm-hmm.
I mean, 14 isn't enough in this case because secretion and absorption happen in complex ways. The one other thing that you might do if you're done and other people, do people who are saying they need more time want to keep working on this for another few minutes? You tell me what is useful for you.
Mine just keeps crashing.
Okay, do you want to show us your code and maybe we can figure that out? You don't have to, but if you'd like
I
to.
was just trying to find the button. So I don't even have, I haven't even been able to make code because I always try to make sure that it's running because it's crashed before, but I launch CompuCell and then just to initialize it, I click that and then just, I've done this like 6 times and it keeps crashing before I even do anything else.
Okay, so that kind of crash usually means that there is potentially a, can you go to the console and see whether it gave you an informative error when it crashed?
Oh,
The console is back behind.
this.
Yes. So it's throwing.
Your project's name starts with the number 1, which isn't a valid Python name. So you need to have it. It needs to start with a character, not a number.
Is there a way to rename it in here?
You have to rename all of the files, and get rid of those periods. It doesn't like that either.
It's the dot that's causing the problem.
Yeah, that's gonna be it. You need to turn make them underscores or something.
How do I change the name?
Save as. Don't use a .xml. Don't. That's a good. No, cancel. But no, don't. Okay, so you're on a Mac, right?
Yeah.
So go to project, save project as. There you go. And now give it a name with no special characters. No spaces and no special characters. There you go.
And then it should run.
Well, it's still going to have that dot in the inherited from the. Still going to have that dot inherited from the. Shoot. See, if you look at the main Python script, the subfiles still have the dot in them because it renamed the whole project, but didn't rename the components.
So should I just recreate the whole thing?
I'm afraid that for this one, it's probably faster to recreate it. And then you can cut and paste things that you've done from there into your other code if you like.
All right.
But the problem is tracking down every place you've got a 9.1 might take a while.
Okay.
But
Make
that's
you feel any better? I made a similar mistake. I had a brief gap in memory and named it the same way I like to name some of my PDFs with the date. So you are not alone, and I will say that it went much faster just to recreate the project.
Yeah, file names with things like slashes and dots are a problem. And the reason that I recommend against things like spaces is that the in principle CompuCell will run on a Mac, a PC, and Windows and Linux. And what is a legal file name is different in those 3 operating systems. And so you're better off being conservative with your file name because it may be fine in Windows to have a space and Linux will gronk on it.
Yep.
And vice versa. Slash may mean something different in a different operating system. And so it's better to not use special characters if you can avoid it.
Yep. When I started
Underscore is all right in all of them, but beyond that.
When I started using CompuCell, it didn't like any spaces on the path at all.
Oh.
So if I had my computer username, name, space, last name, it wouldn't run anything under my documents because the path would be C, name, space, last name, documents, and yeah.
Thank you.
I think that's an inheritance from the original running on Unix operating system, where it was developed because that was spaces were illegal. Windows should allow that, but
It does now. That was back in 3.4, 3.6. I don't know.
okay. Does anybody else have anything they want to talk about and comment on? The moment. I'll talk a little bit and people can keep working at the same time. So the problem was here, which we got. And we compared two examples, which was uniform secretion and constant concentration, that Joel showed us. The next step in this exercise would be to try to use the Python to see what happens if you do secretion inside the cell, inside cell at boundary, inside cell at center of mass, and so on. So why don't people who are still working on the basic one keep working on it, and the people who've already finished that one try doing the Python specification. So that would be the next step. Okay, is that clear?
Yeah.
If everybody can get through the first part, that's great. But let's try. Let's see whether we can get a little bit further, and then after we've done that exercise, we'll take a short break and then come back.
Could you go to that slide that has the how to implement each one of those?
Okay.
Thank you. I think it will make us like faster.
Right.
I think I have it for outside cell at boundary.
Let's see that. I should probably have given each person a task of doing one of those examples. Then we could have compared them. Let's try it. I had just done it, but Zoom and Player were really fighting. So it wasn't recognizing, Player wasn't recognizing my mouse clicks. For some reason okay.
An unintended feature of Zoom, I guess. Okay, can everyone see my? Okay, cool. Glad I'm not sharing my Zoom settings this time. So this is what it ends up looking like, which I think makes sense for how that secretion code is supposed to work. It looks a little funny, but cool.
So it's secreting outside the boundary?
So yeah, I have it set for, outside the cell at the boundary.
Right. So basically you're creating a disk, a ring of secretion. It'll decay inside and outside. And so that makes good sense. Anybody else have something like that they would like to show off? The one that I did, which was the one I was having trouble with I was going to try to show you, and then Player decided it didn't want to play with Zoom. Again, that's one of the reasons I like to do it, the lecture demos on NanoHub, even if NanoHub has its inconveniences, was where you have multiple cell types and you only secrete on contact with one cell type, because it's interesting to see the boundaries. If you do a random initialization, that would be pretty easy to do in your simulation. Create a second cell type, freeze it. In Blob Initializer, create say a 3x3 array of cells with random types. and then have only one cell type secrete and secrete only on contact with the other cell type. Okay. Anybody else have something they want to show for the moment? Is anybody else stuck and needs help? So I'm waiting for an opinion. I can continue, or if people want to keep working on this, that's fine too. You tell me. So not hearing a strong feeling. Again, I started out with a single cell. We had the possibility of constant value, constant flux secretion, and constant concentration secretion. And we already saw the difference between this smooth curve and the flat top curve for constant rate versus constant value. And we noticed that for constant rate, the value is much higher. And it's determined by the ratio of the secretion rate to the decay rate. Here we're using some of these different options, secrete inside cell at boundary and so on. And here are some of the examples that you can get. Secrete inside cell we've already done. Secrete inside cell at constant concentration we've already done. Connor just showed us secrete outside cell at boundary, which is the one all the way on the right. Center of mass gives me a little point in the middle that creates a peak. And inside cell at boundary looks a lot like outside cell at boundary in this case.
Would there be a reason to choose one over the other then, for the inside cell at boundary versus outside?
So biologically, something that I was talking about before is that in reality, getting material across cell membranes is not trivial. And so there's what's called the jump discontinuity, where the concentration will change across the membrane. If it didn't, there would be no reason biologically to have membranes. And so CompuCell doesn't have that built in, again, because the boundary is not an object. Now, in that exercise last week where we built a wall that had a different diffusion constant from the rest of the material, we could see how you got the concentration would go down, then there'd be a jump, and it would go down again. You can do that with a cell. You could define a cell as two compartments, a central compartment and then a ring around it that had different diffusion properties. If you freeze it, it's easy. If you don't freeze it and the cell can move around, then you have to learn how to make a rim of material around a cell that doesn't fall apart, which takes a little bit of work, which is why I don't have that exercise right now. Joel, go ahead.
If you have a different diffusion of the cell, doesn't it make more sense then? Because secreting inside the cell will make it go slower to the outside, and secreting outside would not consider the inside diffusion
Right.
of the cell.
Right. But that's certainly true, and that's something you can do. But there is this issue that in reality, the concentration changes abruptly across the membrane at the boundary of the cell. And that's a little bit harder to do in our world because the membrane isn't an object. But yes, there are games one could play. And that would be, I'd said to Giuliano, he needs to work up some exercises about that. Probably not for this class, but to have available. It would be a good demo to do. Okay, other questions about these possibilities? So that was what I wanted to say about secretion. And now I wanted to talk about uptake. And uptake is more complicated in many ways, both biologically and mathematically. Biologically, cells can do endocytosis, which is what's pictured here, where the cell pulls in a volume of fluid from the outside, surrounds it by a membrane, and pulls it inside itself. You can have chemicals go across the membrane as they do for small molecules like water or glucose. We talked about ion channels and pumps that can move material either from outside to inside or inside to outside of the cell. The other thing that happens pretty commonly in cells, which is really an uptake-only phenomenon, is that cells have on their surfaces receptors, which are molecules that bind to things in the environment. When the molecule binds, it's taken out of circulation. And so that always happens on the outside of the cell. By definition, the receptor is on the outside of the cell. And so that can also lead to disappearance of free molecular species outside the cell. Now, in the case of secretion, we had two options. We had secreting at a constant rate or imposing a value. In the case of absorption or uptake, can we uptake at a constant rate? Does it make sense to take up at a constant rate?
I don't think so, right?
Well, what would happen if we took up at a constant rate?
Taking up at a constant rate, just like assuming there's a finite amount of chemicals, then you're going to be making it more and more sparse in terms of so it seems, unless you're putting in more effort as you're going, yeah, you could keep it constant for a bit, but that isn't sustainable.
Well, if we literally mathematically keep taking up at a constant rate, the concentration will go negative.
Right, yeah.
Which is not allowed to do if it's a concentration. Again, there are other things, there are fields where it's allowed to go negative, and that might be possible. But for chemical, no. So the rate at which a cell takes something up is complicated. And if you ask the question, if I put a cell in 0.1 millimolar glucose, and I ask what fraction of the glucose in the environment is being taken up, the answer is nobody can tell you. So actually the rate at which cells take things up from their environment is some complex function of the internal state of the cell, the concentration outside the cell, whether they're pumps, whether there's endocytosis. Endocytosis, I go in and I swallow a volume of material from outside. So whatever is there, I take in. So in a sense, that one is simple. But if I have diffusion across the membrane of the cell, that diffusion rate should be set by the difference in concentration between the concentration outside and the inside. That's called Fick's law. It should be proportional to that. And that's something we don't have implemented in CompuCell. We don't have a Fickian diffusion. There should be a possibility to define the internal concentration, the external, and define the flux. That's what I was saying we could probably do by hand. And the other thing that happens is there's saturation. So if the concentration is very small outside, the uptake rate is small. As the concentration goes up, the uptake rate goes up, but there's some maximum uptake rate. And so typically there'll be some kind of saturation function we haven't really explored Hill functions in detail, although we've used them once or twice. But there are many possible dependencies on external concentration that we could have. And so there are going to be potentially a lot of variability in how we do uptake. But we are going to do it in a rather simple way. The simplest thing we could assume is that our uptake is some fraction of the amount of the chemical that's out there, something that looks like first-order decay. That way our concentration is guaranteed never to go negative. And in fact, if we don't want to monitor how much we're taking out of the system, we can do uptake by creating a decay coefficient that depends on the cell type. So if we imagine the bacteria taking up chemical field, we could say decay coefficient cell type bacterium 0.00001 here. Every time step, the bacterium destroys 1/10,000th of the chemical that's available to it. That's a perfectly legitimate way of doing things. It's not very flexible, but it's actually not a bad way of doing it. If we are going to use the options for secretion and absorption, the same thing, which is called the secretor object, also lets us do uptake. And CompuCell doesn't support all those complex functions and doesn't support Fickian uptake, which are defects, perhaps. But what it does do is give us a very, very simple idea, which is not unreasonable, which is if the concentration is small, we take up a fixed fraction of what's available. And then there's some hard maximum, which is the maximum rate of uptake. And so when we specify uptake, we are going to specify two numbers, one of which is the maximum amount we can take up, and the other one of which is the fractional amount that we're going to take up to that maximum. Does that make sense to people? If I set the maximum to be infinite, then I would just take up a fixed fractional amount. That would be equivalent to decay. If I make the maximum small, very small, then I'll always take up that maximum until the concentration goes to zero, at which point the amount I take up goes to zero. So I can more or less get my two limits out of that. One thing that you have to be aware of when you use total count, you are likely to discover that the amount returned is a negative number. And so you better check whether the amount returned is positive or negative. Again, in this case, we have all of our possibilities. If it's something like glucose or water or oxygen that diffuse across the membrane, then it makes sense for the uptake to be happening just inside the membrane. So this uptake inside cell boundary is really designed for uptake more than secretion, but to be symmetrical, we do both. Again, the syntax looks very similar, except that secrete is replaced by uptake in the command. And we can do the same thing on contact with all of the various options. We can, if we imagine that what's happening is that there are receptors on the outside of the cell that are pulling the chemical in, which certainly happens for a lot of signaling molecules in particular, then it makes sense to have the uptake happen just outside of the cell. And we have the same set of commands there. And we have the option of uptaking everywhere over the surface of the cell. That maybe makes more sense in 3D than 2D than 3D. And if we want to be perverse, we can try to take everything out at one point in the center of the cell. It doesn't work very well for secretion. It works worse for uptake. And the earliest versions of CompuCell, that center of mass one was the only one we had, and it was not very much fun to work with. But again, for orthogonality, we support all of them. Okay. Any questions about that? I tried to make things as parallel as possible between the two cases. So why don't we try doing that now? Why don't we take a 5-minute break, maybe? I'll leave this up. What I'd like you to do is now create a lattice with a single frozen cell, so you'll use the same simulation you had before. And we will have that cell take up inside the cell at the boundary, at the center of mass, and outside the boundary. And I want you to try to compare things. And clearly, in this case, you need to have some source of chemical, because if you have no chemical to begin with, nothing will happen. And so there are a couple of ways you could do that. You could start out with a constant concentration of chemical everywhere by initializing the simulation to have a value of, for example, 1 everywhere in your field initializer. You could use constant value boundary conditions on your array. And so I would suggest one of two things. Either use periodic boundary conditions and start with a fixed amount of chemical everywhere, or use constant value boundary conditions and start with a constant value, the same constant value everywhere. So you start with a uniform initial value, and then you start pulling chemical out. In one case, you have no source of additional chemical, so the total amount in the whole system will go down, and you could use that total amount reporter for the whole field to monitor how it decayed in time, if you wanted to. In the other case, because you're continually sourcing material from the edge, you should reach a steady state where the boundaries stay at the value you started with, and then the middle comes down. So is that?
I think I have it for uptake inside cell.
Does anybody else have it? How's it going? Okay, Connor, do you want to show us what you've got? Maybe show us the code that generates it. That would be great.
I'm muted. Would you like me to show the code first or the output first?
Why don't you show us the output first and then the code?
Okay. Can everyone see the plots? All right. It's not the fastest simulation, but it's not the slowest one either. So I did constant value of the chemical gradient on the X and Y minimum, and then I did periodic, just because the way that it's reading is just along the X location. And it very, very slowly will eventually get there. If I had done a constant field, this would have been faster, but I was already in too deep. Or not a constant, but like an initial condition with everything spread everywhere. But you can kind of start to see it here. We start to see like a warping and a bend, and we can see that it's not moving forward at the same speed, and eventually it just wraps around the entire cell. Still running. Yeah, it's. I think it's just going to be painfully longer if I keep letting it go, so I can stop it there. And then far as Twitter goes. So this is just, once again, initializing the plot the same way that we've been doing it for the past couple weeks. And then I have the secretor uptake inside cell with the max allowed amount, which is where it plateaus, and then the relative amount. And then I think, is there something specific otherwise that people want to look at? I feel like, besides that, I actually messed up. I didn't initialize the secretion plugin, which is what gave me trouble for a little bit, because I wasn't thinking straight that I would need secretion for the uptake, but that is necessary.
Okay, did everybody follow that? I think that was a good explanation. I wanted to try to show you something else that we talked about as a possible thing to do, and then didn't actually do. And I'm having the same odd bug that some other people reported, which is that when I stop player and start again, it loads it runs the previous simulation. I have no idea. That's a new one to me. Giuliano, can you document that? And it's rather odd. Instead of loading the new version, it loads the old one. So this may or may not display because I've been having this issue with the screen share. But let's see if I could get it to work. So do you see my CompuCell player? And so what I've done here is I've created an array of 2 cells. And I've said that I only secrete one cell type secretes on contact with the other. And you see here, this is in a sense doing what Joel asked about. What if you had different secretion in different places on the cell surface? You see that, Joel? So you see I get this quite messy pattern where I'm secreting in these particular boundaries. And now let it run. And you'll see that the pattern is smoothing out because the diffusion length is long compared to the size of the cells. Now, if I'm inside this cluster, I'll see that I really do have a shape that's not a circle. So the concentration is variable dependent on where the secretion has happened. However, if I'm outside of it, say over here, I can't tell that the secretion isn't just from a point source in the middle. And so I could take a simulation like this, change the diffusion length, and ask the question, when does it matter that I have multiple sources or not? And I've saved this example in that demos folder. So if people want to play with that, they've got it available. And I do apologize about the issues with the display here. All right. So here's what I did for that first example. I created global diffusion constant, global decay constant. Here I set the boundary values to be 10. And if my cell absorbs, then I get eventually a inverted parabolic concentration, which is 10 at the boundaries and substantially less in the middle. We could play with, and I don't think I want to do too much of that tonight. We could play with using secretion and absorption at different places. And maybe let's look at the results first and then come back and have you try it out a little bit. As you'll see, the possible shapes that you get with absorption are rather more complicated than the ones you get with secretion. This was secretion inside cell at boundary, inside cell at center of mass, outside cell at boundary, which is almost indistinguishable from inside cell at boundary. Where is this asymmetry in the chemical field coming from? It's coming about because my square here is not perfectly centered on the lattice. And so it's not symmetrical relative to the source. If I change the saturation term, I could get additional shapes, and that's something that one could play with. Another one that we could try, which is interesting, is having the medium secrete. Here we could have the medium have constant concentration. In that case, I recommend using periodic boundary conditions. And then we can have our cell do its various kinds of uptake. Here's inside the cell, we get that parabolic trajectory that we'd expect. If I use inside cell at boundary, I get an abrupt cutoff there. At the center of mass, I get linear gradient. And outside cell at boundary, I get something again that looks a little bit like inside cell at boundary. And so, as I mentioned before, there is a rather complicated set of possibilities here, which depend on the biology and physics that I'm trying to replicate. So the next one that I wanted to do was, how did people do with that homework assignment? Because this is fundamentally that problem in the homework. And I know some people said that they were having some difficulty doing it. If everybody got through it all right, then that's fine. If there were people who had issues with that, then I would think we should probably do it together. So you have to tell me what's useful to you.
I think the most of the problems were related with the code snippet. There was like a little bit of a, it's missing parts on the code snippet. So I can see how that would, block some people.
So yeah, that was, well, actually the previous thing, I don't even know what gave me trouble. I just ended up restarting the project because I got a very bizarre output. But I think in the second reading, I went back to it and they showed where it was supposed to go. So I was able to figure it out a few hours before earlier today.
Okay, we have 4 more people in the room. I want to make sure everybody was able to get through that homework assignment. If you weren't, that's fine. We can go through it step by step here. If you've done it, then I think it's probably not such a bad thing to play with it. The goal of this assignment, the homework assignment, was to do uptake limited growth, which is really how tumors work. And that's a relatively sophisticated assignment. It also includes the idea that different regions of the tumor behave differently. In particular, and we'll come back to this a little bit later, the tumor consists typically an avascular tumor, early tumor that does not have blood vessels, will consist of a surface layer of cells that replicate rapidly and use up a lot of oxygen, a layer of cells that are just inside of that surface layer that are alive but not replicating and use less oxygen, and then a cluster of dead and dying cells in the middle that are basically passive. They're deteriorating and disappearing slowly, but they're not using up any resources, and they're not dividing. And so I've talked before about the idea of trying to do simulations in pieces where you could validate each part of the simulation separately. And so if I were going to do this simulation of proliferation, the first thing I would do would be look at the chemical fields. And so the way I would recommend doing that, and that's what this exercise is about, is to create 3 concentric layers of cells, which are frozen, which are not going to grow, shrink, or do anything else, but which are going to take up the chemical from the environment. And then I think I would look at the chemical concentrations when this happens and ask the question, can I adjust my parameters to make the chemical concentrations reasonable? And by reasonable, I don't mean that we know that the exact oxygen concentration is so many millimeters of mercury, but rather the oxygen concentration at the middle should be half of that at the surface, or a third of that at the surface. The oxygen should penetrate 1 cell depth, 2 cell depths, 3 cell depths. So mainly you're asking questions about relative values and distances over which things change. And as we know, those have to do with two numbers, the diffusion length and the diffusion time. And so I'd ask you to try this exercise. What I'd like you to do is create, use Blob Initializer and draw 3 layers of frozen cells. You can give them names. I call them quiescent, necrotic, and proliferating, or the necrotic in the middle, quiescent and proliferating cells. And then define constant value boundary conditions on the lattice, and an initial concentration equal to that value. That's what we were talking about with Connor. And then initially say the diffusion field has the same diffusion constant everywhere, but that the decay rates are different. We'll say that in the proliferating cells, well, let's start out with everything being the same. The decay rate and the diffusion constants being the same. I've got 2 values here, 30 and 10, gamma of -10 to the -3, 10 to the -2. You could work out what the diffusion lengths are, and then run the simulation and see if the diffusion length is validated.
Also, sorry.
And then for people who get a little bit ahead, you could say, okay, don't have the necrotic cells take up the concentration, and see what happens then. And this is a problem that one could do a lot with, but let's see if we could get the basic simulation working. And people should remember how to do Blob Initializer. One thing to remind you about with Blob Initializer is that it's executed sequentially. So if you want to draw 3 concentric blobs, draw the outermost one first, then draw the one inside of it, and then draw the one inside of that, because each one will overwrite the previous one. Okay? So why don't we if there are any questions about the assignment, please ask. Giuliano, I'll let you do since I'm having trouble with Twitted and playing nice with CompuCell, I'll let you do this one in real time, so that if we need to show it, we can show it. So I'll give you a few minutes to try that out. And feel free, Joel, go ahead.
Yeah, a couple of things. We're still doing 2D, right? Although the word layers is like just side by side, right? On a 2D space. Should they be touching each other?
So let me find a. Actually, I forgot. Annotation is available again. The for a while Zoom was blocking annotation, and now it's back. I don't know why they turned it off, and I don't know why they turned it back on, but they did. So let me turn on annotation. So what you want is this would be proliferating, this would be quiescent, and this would be necrotic. Okay? Is that in 2D? If you do it in 3D, it will be exactly the same in terms of its results, but it will run a lot slower. Any other questions?
I just want to make sure that I was looking. This is a different version of the problem that was on the homework, right?
The homework problem went further with it. And so it may not be identical.
Okay, I feel like maybe I'll need to make sure I'm looking at the right version of the homework then. I think, unless I misread it, the one on the homework didn't specify doing 3 different cell types, which is what threw me off. But that might have been a me error.
No, well, I'd have to look back at the homework problem because I don't have it open in front of me. It's quite possible that, I mean, the simplest thing to do would be just to draw a blob, have it absorb, and see what happens. And then the next step would be to divide the blob into 3 domains and then see what happens. And then the third thing to do would be to say the cell types could change depending on the oxygen concentration to see how the width of the blobs change dynamically. And then the last thing would be to have them grow. And I think I left out the second to last one in the homework. I jumped. Any other questions about this? Again, I want to make sure that everybody's able to work with these effectively, because I realize that it's challenging there's a lot to learn. We can always make these exercises clearer. I've said before, if people catch mistakes in the homework or have suggestions for making the homework problems clearer, please do let us know. We do update them. So are people ready to give this a shot? So I'll start the poll, but don't feel you have to answer the poll immediately. Just unless I start talking again, you could just answer the poll when you're done, so I can keep track of who's successful. Josh, question.
Yeah, I'm just a little confused. So the picture makes it look like that the layers are supposed to be different sizes, but the first instruction is to make each layer 8 by 8. So
no, the cells are 8 by 8. Each cell is 8 by 8. I didn't tell you how big to make the layers, so you can choose.
okay, and also can they overlap, or do they need to be like donuts?
So if they're frozen, it's all right to have overlap. At any given position, you can only have one cell. So if you draw the biggest circle first, and then you draw a smaller circle on top of it, at the boundary of the smaller circle, the cells from the bigger circle will get fragmented. You'll get pieces of them. And for the purpose of this exercise, that won't cause a problem. There are ways of doing it that are cleaner, but that's a good question. And if we did this with dynamic cells that were not frozen, then we would see that we would get some irregularities from doing it that way. Any other questions? So we haven't played around that much with Blob Initializer. For people who've got the basic exercise done already, try changing the diffusion constants and the decay constants, and also try changing the diffusion and decay constants of the various components of the tissue. So you could have all the absorption happen in the center, or all of it happen at the edge, and see what the chemical concentration looks like when you've done that. As I mentioned, this is a very rich problem, so one can spend really quite a bit of time exploring it. It's not a simple result. Giuliano says he has it running, so would people like to see his results? Because we're going to run out of time, so I want to make sure everybody sees there's a version of this that's saved as avascular tumor in the demos. So Giuliano, do you want to take it away for the rest of the class?
Yeah, not sure how the share is gonna look because Compressor is not looking too great. But yeah, this was an example that there we go, that we did for the workshop a while back, and it was what you're trying to do. So we do have some proliferating cells still at the edge, then a ring of quiescent cells, so cells that are just chilling, and a necrotic core. I can set this to run, but as it is, it will take over 500 steps for anything to actually happen. So not very fun to actually watch. But I can show you the code and the logic for it.
I think this version, the P1, has differentiation based on oxygen concentration.
Yep, that's right.
So that's a little bit more sophisticated than the base model.
Yep. So in this case, we have 3 cell types, proliferating, quiescent, and necrotic, and they are all frozen. And because they are all frozen, we don't even need to care about the contact energies. Then I have the secretion plugin that I'm setting up purely in Python, and the oxygen field, which controls if the cells are gonna stay proliferating or quiesce or die. In here, I have the whole field starting at 100, meaning 100% of whatever. And all of my boundary conditions are of constant value at 100. And then in the steppables, what happens is I have a few thresholds for when, well, first I have the uptakes of the proliferating quiescent cells. In my case, I have the quiescent cells uptake half as much as the proliferating. And the relative uptake is in case there is less than 1 unit or 0.5 units of oxygen in the cell. And also some thresholds to go to quiescence or necrosis. And they are, yeah, so 35 is a bit more than E times 100, which is gonna be the, so one diffusion length away from your source, you're gonna have E times the concentration at the source, if I'm not mistaken. And so I wanted to have the proliferating ring be around 1 diffusion length, although I think it's shorter than that. And so I set it to be a bit bigger than the theoretical 100% accurate value. And then for every step in the simulation, I get the secretor for my oxygen field. Then I go over my proliferating cells and I uptake around the whole of the cell, the uptake value, which was 1. And if it's less than 1, it gets 0.2 times 1. And because I'm doing uptake inside a cell, I'm actually gonna remove from the oxygen field the this uptake rate here times the cell volume. But since this is 1, I'm taking out the cell volume from the cell field. Then I go over the quiescent cells, do the same thing. Necrotic cells don't uptake, they are dead. And then I am also counting the number of necrotic cells, probably to do some plotting. Then I once again go over the proliferating and quiescent cells. And this was before we had the amount the cell is exposed to function. So in here, I'm sampling from the center of mass of the cell. In your case, you have a more sophisticated way to do this that wasn't available. And then I do a bunch of checks of the concentration against the thresholds. First, I check if they're gonna be necrotic, then if they are gonna be quiescent. And in my case, quiescent cells can become proliferating again. And never necrotic, because I'm only going over the proliferating quiescent. So no necrotic at the start, and then it can become necrotic here, but I already checked that this value is below the lowest threshold, so this will not be activated. So it's sound code. I needed to double check just now. And yeah, that's it. And we get the rings, or sort of rings.
So the one thing that's missing here is the profile, the concentration profile.
Yep.
I have a question about best practice on the code, because I saw that everything that you set it up was already on the Python code. And I think it's because, I don't know, I can read better on the XML, but there is anything that you guys suggest as the best practice? I would like to just work in one file, to be honest.
I prefer to do it all in Python. Well, so if I had set it up in XML, I would have a bunch of tags here, which is probably what you have. But in that case, you can only set the secretion attributes on a per cell type basis. If you just have the plugin secretion open and close tags, CompuCell is gonna know to load it up, but it's gonna leave all the specifications to be in Python. And then in Python, you can do it in a per cell basis, which I think is, I don't want to say better, but more convenient. a lot of situations.
I actually had a question on that. Have you actually checked that? If you put the per cell, if you put the specification in the secretion plugin,
Yep.
and then you change individual cells, what happens?
It overwrites, I think. I think I tried that.
Yes. Okay.
I think it works.
Okay, that's good to know. I wouldn't know. Because I found that for the volume, it doesn't quite work. If you
No,
try
for
to-
volume it doesn't, but I think for
Ah.
secretion it does.
Okay, so I knew that for volume it doesn't work, and just assumed it was gonna be the same.
Yeah, but if you can, I don't know if you can. If you should try. Don't trust me.
Okay.
Check that, please. That's a request.
Yep. Let's see.
I mean, here the issue is you'd have to change the individual cell properties one at a time, so not have them all the same. Because in the Python here we're making them all the same. Any other questions on this? I know this is a somewhat tough problem to do, but I think it's one of those things where it requires an effort to get through it. Once you've gotten through it, you've got a lot of basics under your belt. And so, and I think it's important to try to do it on your own as well as watching people do it, because it does teach some critical ideas.
It's something bigger, more. I don't know. But I have the green cells uptaking from oxygen in Python, and in the XML they are secreting. So let's see. Okay, it does increase. Makes sense because my secretion was faster than the uptake. If I go to less than the uptake, so it's not a pure overwrite, but maybe doing both. Yeah, I think it does both. Five. Start to go up. Yep. So it doesn't override, but it allows you to do both, which I'm not sure is the best thing to happen. Easy for mistakes to appear.